There is a place on Earth where gravity is weaker, not in a way that you would feel walking around, not dramatically, but measurably, precisely, confirmed by some of the most sensitive instruments ever placed in orbit, a region covering millions of square kilometers where the gravitational pull of the Earth is consistently, measurably lower than the models say it should be. The region is called the Hudson Bay Gravity Anomaly. It sits over the Hudson Bay area of Canada and extends across a significant portion of the country's landmass, and the fact that it exists at all raises questions that go deeper than you might expect, questions about the interior of the Earth, about the aftermath of the last ice age, and about how well our models of the planet we live on actually reflect reality. This is not a fringe theory. This is not a conspiracy. This is documented, measured, peer-reviewed science that most people have simply never heard of. And the reason it matters goes beyond being an interesting piece of trivia. Stay with me, because the layers of this go somewhere most people never expect. Let's start with something that most people take for granted. Gravity is not uniform across the Earth. Most people think of gravity as a constant, a fixed force that pulls everything downward at the same rate everywhere on the planet. That's not true. Gravity varies depending on where you are. The Earth is not a perfect sphere. It bulges at the equator and flattens at the poles. This means that someone standing at the equator is farther from the center of the Earth than someone standing at the North Pole. And because gravity weakens with distance, people at the equator experience very slightly less gravitational pull than people near the poles. This is well understood, well measured, and accounted for in everything from GPS satellites to precision engineering. But there are other variations in Earth's gravity that are less intuitive and less well understood. Gravity also varies based on the density and composition of the rock and material beneath you. If you're standing above a region of dense rock, iron ore for example, there is more mass below you, and gravity pulls you slightly more strongly. If you're standing above a region of less dense material, ocean water for example, or sediment, there is less mass below you, and gravity pulls you slightly less strongly. These variations are called gravitational anomalies, and they are real, they are measurable, and they have been mapped with satellites with extraordinary precision. In the early 2000s, NASA launched a pair of satellites called GRACE, the Gravity Recovery and Climate Experiment. These two satellites flew in orbit in tandem, separated by a precise distance, and measured the tiny changes in that distance caused by variations in Earth's gravitational pull below them. As the satellites flew over regions of higher gravity, they would be pulled slightly forward or backward, changing the distance between them by incredibly small amounts, millimeters, sometimes less. By tracking these changes, scientists could map the gravitational field of the entire Earth in more detail than had ever been possible before. What the GRACE satellites found confirmed something that had already been suspected from older measurements, but had never been mapped so precisely. The Hudson Bay region of Canada has measurably less gravity than the global average. Not a little less, enough less to be significant, enough less to require explanation. The anomaly is not subtle by scientific standards. In the Hudson Bay region, the gravitational pull is approximately 25 to 45 milligals below the global average. A milligal is a unit of gravitational acceleration, 1/1000th of a gal, named after Galileo. The number sounds small, but it represents a real, measurable difference in the force pulling you toward the center of the Earth, depending on where you're standing. So, what is causing it? Two main explanations have emerged from decades of scientific study, and this is where the story gets interesting, because neither one fully solves the problem. Both are probably contributing, but the exact balance between them and whether there are additional factors not yet accounted for is still being debated. The first explanation is called glacial isostatic adjustment, and to understand it, you have to go back about 20,000 years. During the last glacial maximum, an enormous ice sheet covered much of North America. In the Hudson Bay region specifically, this ice sheet was approximately 3 to 4 kilometers thick in places. 3 to 4 kilometers of ice piled up over millions of square kilometers of land. That is an almost incomprehensible weight, and like anything under enormous weight, the Earth's crust bent under it. The underlying mantle, the viscous, partially molten rock layer beneath the crust, was pushed aside. The ground literally pressed down, and the mantle material that had been there flowed away in response. Then, approximately 12,000 years ago, the ice melted, the weight was removed, and the mantle material that had been displaced began, very slowly, to flow back. The crust began, very slowly, to rebound upward toward its original position. The key word is slowly. The mantle is viscous. It doesn't flow like water. It flows like an extremely thick, hot solid under immense pressure. The rebound process takes thousands of years, and the remarkable thing, the thing that directly connects to the Hudson Bay Gravity Anomaly, is that the process is still happening right now. Thousands of years after the ice melted, the ground in the Hudson Bay region is still rising, still rebounding, millimeters per year, measurable by modern instruments. And because the mantle material has not yet fully returned, there is less total mass in the region than there will be eventually, and therefore less gravity. This is the glacial rebound explanation. It is well supported by data. The rate of ground uplift in the Hudson Bay region matches predictions from models of glacial isostatic adjustment. The spatial distribution of the gravity anomaly overlaps with the extent of the former ice sheet. It is a compelling, scientifically mainstream explanation, but it doesn't fully account for the entire anomaly. The numbers don't quite add up. When scientists model the expected gravity reduction from glacial rebound alone, the predicted anomaly is somewhat smaller than the measured anomaly. Something else is contributing, and that something else is the second explanation. The second explanation involves convection in the Earth's mantle. This is where things get significantly more complicated and significantly more uncertain. The Earth's mantle is not static. It is in constant slow motion, driven by heat from the core, moving in enormous convective currents, like the currents you see in a lava lamp, but operating over geological timescales of millions of years. Hot mantle material rises, cools as it approaches the crust, and then sinks back down. These convective currents are the engine that drives plate tectonics. They are the reason the continents move. But these currents also affect gravity. When a region of the mantle has a downward convective flow, when material is sinking rather than rising, it pulls the crust slightly downward and creates a region of slightly lower mass near the surface. And some models of mantle convection suggest that the Hudson Bay region sits above a zone of downward mantle flow, contributing to the gravity anomaly independently of whatever is happening with glacial rebound. The problem is that mantle convection is extremely difficult to model precisely. We cannot directly observe the mantle. We cannot put instruments inside it. We infer its behavior from seismic data, from surface measurements, and from physical models based on what we understand about the composition and behavior of rock at extreme temperatures and pressures. And those models, as the Kola Super Deep Borehole demonstrated decades ago, do not always match what we actually find when we look directly at what's underground. So the current scientific consensus is that the Hudson Bay Gravity Anomaly is caused by a combination of glacial isostatic adjustment and mantle convection, but the precise proportions, how much of the anomaly is from the Ice Age and how much is from deep Earth processes, is still being worked out, and the possibility that there are additional contributing factors not yet identified
cannot be ruled out. Now let's talk about why this matters beyond being scientifically interesting. GPS satellites and navigation systems have to account for gravitational variations across the Earth's surface. If you use a GPS receiver anywhere on Earth, the system that calculates your position is using a model of Earth's gravitational field, a model that includes anomalies like the Hudson Bay region. If that model were wrong, or if the anomaly changed in unexpected ways, the calculations would be off. The precision of modern navigation depends on the accuracy of our gravitational maps. Geodesy, the science of measuring the Earth's shape and gravitational field, is foundational to everything from surveying property boundaries, to tracking sea level rise, to monitoring changes in ice sheets. The GREC satellites that mapped the Hudson Bay Anomaly were the same satellites that provided the most detailed measurements of ice sheet loss in Greenland and Antarctica, contributing directly to our understanding of climate change. The technology is connected in ways that make the Hudson Bay Anomaly relevant to some of the most pressing scientific questions of our time. And then there's the deeper implication. The Hudson Bay Gravity Anomaly is a reminder that the Earth is a dynamic system, still changing, still moving, still adjusting to events that happened thousands of years ago. The ice that created the anomaly melted 12,000 years before any of us were born, and the Earth is still responding to that event. The mantle is still flowing back. The crust is still rising. The gravity is still shifting, slowly, toward whatever the new equilibrium will eventually be. The Earth doesn't work on human timescales. It doesn't care about our categories of past and present. Events that happened 12,000 years ago are still unfolding in the geology of the Hudson Bay region right now. And when we point instruments at the sky and measure the gravity of our own planet, we are measuring the echo of an ice sheet that no longer exists. There are other gravitational anomalies around the world. The Indian Ocean has a significant negative anomaly, a region where gravity is weaker than average, centered approximately south of the Indian subcontinent. This anomaly is larger than the Hudson Bay Anomaly and is thought to be related to mantle convection patterns in that region. The exact cause is, again, not fully resolved. There are positive anomalies, regions of stronger than average gravity over certain mountain ranges and dense rock formations. There are anomalies over ocean ridges where new crust is being created. The gravitational map of the Earth, when you look at the full picture from the GRACE data, is not a uniform sphere. It is lumpy. It is irregular. It is a record of everything that has happened to this planet, every ice age, every mantle current, every collision between tectonic plates, written in the language of gravitational force. We think we understand gravity. We have understood it mathematically since Newton. We have refined that understanding through Einstein and general relativity. We can use it to navigate spacecraft to the outer planets with extraordinary precision. But when we look at the specific, detailed behavior of gravity on our own planet, where the ice sheets were, where the mantle is flowing, what is happening in the crust at this exact moment, we find that the picture is more complicated than we expected, and that there are pieces of it we are still working to understand. The Hudson Bay region has less gravity than it should. The planet is still recovering from an ice age that ended 12,000 years ago, and the instruments we've built to measure it are revealing a portrait of the Earth that is stranger, more dynamic, and more uncertain than most people realize. The sky still hides secrets, and this is just the beginning. Subscribe to Fact Harbor for more mysteries.